All right. Unfortunately, I changed versions of R between Monday and today while trying to help the student, and I'm now having to reinstall a couple of programs. So while I'm waiting for that to happen, do you guys have any questions over what we did on Monday? Yeah.
I have a question about the homework actually.
Yeah,
So
I
I
can do
saw
that too.
that went up like last night-ish. After that.
No, it went up Monday,
Oh, okay.
Monday morning early.
Okay. I'm just
Yes.
saying, so we performed the Anova,
Mm-hmm.
then you said if like there's a question that was like if there's a significant difference from the post-hoc analysis.
Yep, that's the Tukey's analysis. We went through that in class.
Right, right. Could you walk us through that again?
Yeah, sure.
Just very quickly. And then would we do that on R or would we do that?
You can do it by hand. I showed you how to do it by hand.
Okay.
Let me go pull up the PowerPoint. But yeah, we can do that. So once you have a significant result, basically, Tukey-Kramer's test essentially calculates what the minimum significant difference is for you to say that there's a difference between two means that you're comparing to one another. And you calculate the minimum significant difference by getting the critical value and the standard error. The critical value comes from a table, which I need to give you, I guess, if I'm going to have you guys do that. I forgot about that. There's a critical value from a table, so my book of statistical tables, there should be a table in there for that. So you have the numerator degrees of freedom and the denominator degrees of freedom, just like you do when you're running an F test at the end of Anova. And then the standard error is the mean square within value, but then that's corrected for sample size. So in some cases, the samples are the same size, and so it's just like 1/10 plus 1/10. But in the event that you have two different sample sizes for two different treatments, this standard error value might be different for each comparison depending upon what the sample sizes are of the two treatments that you're comparing. So this is the standard error, and then you just can basically create a table that gives you treatment A, B, C, and D versus A, B, C, and D. Clearly, on the diagonal, these are all, well, they're just nothing. They're blank because you can't compare A to A, B to B, C to C, etc. And what I typically do is I'll calculate whatever the minimum significant difference is, and I'll put the MSD for the comparison of A to B up here, A to C here, A to D here, and then the actual observed difference are here. Wow, I didn't draw my table very well. And essentially, if this is bigger than that, then that's a significant difference.
Oh, okay.
So that's,
So the observed difference is just the one mean minus the other?
yep,
Okay.
yep,
And then the minimum significant difference
is this Q multiplied times the standard error, and this is how you calculate the standard error.
calculate a different one for each set.
It depends on whether or not you have everything that are all the same sample sizes. If these are all sample size of 5, then it's going to be the same number. If one of these treatments is 5 and one of these is 10, then and all the rest of them are going to be 5, then all of them are going to be the same, except anytime you're comparing B to something else.
Then it would be 1 over 5 plus 1 over 10.
Yep, exactly. Yep. These are for the treatments you happen to be comparing at that moment. So the reason that I make this table this way is so that I can see if the minimum significant difference changes because sample size changes. And then it's just a matter of Is this one bigger than that one? Is this one bigger than that one? Is this one bigger than that one? So, and so for the example that we were working, these were all the same size. These are all sample size 10. And so the minimum significant difference is 2.97 for every one of them. And so then the question is, well, is this observed difference between the control and glucose added, is that bigger than 2.97? Is the difference between control and fructose, is that bigger than 2.97? Bigger than 2.97, bigger than 2.97. 1.1 bigger than 2.97? It's not, so it's not significantly different.
Okay.
Yep.
Thank you.
Sure. So the nice thing about this, so right now we're going through the P's analysis in R. At the end of the P's analysis, what we're going to do is we're going to do post-hoc tests. When we do those post-hoc tests, the output that R gives us should be the same as the output that we calculated by hand. And that's the whole reason of working examples out by hand and then working them on the computer is you can see what the computer is doing, and then you can verify to yourself that the computer is actually doing that. I don't really care about P's or P growth or anything else. This is just a nice, small, tractable example that we can look at. All right, so let me get caught up with you guys. Hopefully you guys have been through this whole thing. Yeah, okay. So we are at the point where we've done the Shapiro-Wilk test. William, is William here? Yeah, William. Can you remind us how we did the Shapiro-Wilk test? Yeah.
So we first the analysis of the treatment data.
Okay. So this is setting up the analysis. So now this is just kind of in our R's memory. Whenever we type in the word analysis, it's going to do this analysis for us. Why did we do that? Because we just ran an Anova, basically. Why did we do that? Not so much for Shapiro-Wilk test. Why do we need the model specified for the Shapiro-Wilk test? Yeah, but what is the model going to give us? Claire, help him out. We are trying to get all the residuals. And so what we do is we run, well, where did I go? We run the analysis, but we are running the analysis so that we can get the residuals, because it's the residuals that we're going to use to actually test for normality. Somebody else, why do we use residuals of the entire data set across all treatments to test normality? Yeah.
Isn't it because if we only did, what would it be the means of the 4 or 5 treatments? If we did that, we have a lot less statistical power than if we have, say, 50 residuals.
Yes, exactly. And so we improve our ability to find deviations from normality if they occur by basically looking at normality across the entire data set rather than just looking within each treatment. We could do it within each treatment. We just might not find a difference between the normal distribution and the observed distribution simply because we don't have a big enough sample size.
And we're doing that like within each like treatment. We're doing that by just using their sample mean, right?
Yeah, so it's the difference between the sample mean and the data set,
right.
The individual data points, but that's within each treatment.
Right.
You don't do that to the grand mean, because if the sample mean is close to the grand mean, then all those points are going to be close to the grand mean as well. And so as you get bigger differences between treatments, if you're doing it with the grand mean, you're going to get bigger values of residuals. And you see, once again, let's not do head dat, let's do view dat. So we see that all of these residuals are fairly small, but they are all in the same range as we go from one treatment to another. And the reason for that is because we're comparing those residuals to the sample mean, not to the grand mean. And that's what we want to be doing. So that handles one of the assumptions. What's the other assumption that we need to test? Sabrina, what's the other assumption we need to test? Yep, we just did normality. If you can't remember the name, describe it. Nope, not residuals this time. Mallory, help her out. What's the other assumption that we need to test? It is the homogeneity one. Homogeneity of what? Of variances, yep. Tyler, describe to us what the homogeneity variances actually does in terms of how it goes about testing for differences among variances. Nope, it isn't a normality test. Trenton, help them out. Yeah, what actually is the homogeneity of variances looking at?
The t-test.
It's not a t-test. It's an Anova, but it's an Anova on what? I don't even know what that means exactly. So we can do an Anova on the raw data. We can also do an Anova on what? What's going to tell us about variation around the mean? It might be residuals, but in this case, it isn't residuals that they use. What does Levine's test use instead of residuals? It's not the standard deviation. So when we have a sample mean and we have the different values we can have the mean and we can calculate the residual, which is just the distance between these things. And that's how that's the raw data that we use for testing for normality. Now, one of the things that we could do with Levine's test is we could just get the absolute values of these residuals and say what magnitude is the total variation away from the mean. But actually, we don't compare these values to the mean with Levine's test. What do we compare them to? Somebody said it. Who said it? What'd you say? You compare them to the median. And so the mean is the mathematical center of this. The median will be different depending on whether or not your data set is normal. So if you have a skewed data set, if your data set comes from a distribution that looks like this, you're going to have a bunch of values that exist down here because those values are common, but you'll have a couple of values that exist up here. And what happens when that happens is it pulls the mean upwards in value. These couple of extreme values pull the mean upward. And so your mean, your sample mean for the sample might be here, but the median will be a little lower because that represents where 50% of the population is here and 50% of the population is here. So what Levine's test does is it essentially does an analysis of variance on the absolute values of the deviations of the actual values from the median of the sample.
We do that to determine whether variance is homogeneity variance?
Yep, yep. If there are differences among the treatments in the magnitude of that difference, and that's why we use the absolute values, because once again, because some of these deviations are going to be positive and some of them are going to be negative, they'll tend to cancel one another out. So we make them all positive. So we take the absolute value of the deviation of the data point from the median, and then that's the value that we analyze. And we're just looking to see if the treatments are different in terms of the magnitude of those differences. Yep. So that's how you would do it by hand, but the way you do it here is we just write a simple line of code. So get yourself a new chunk of code. Once again, why am I giving myself little titles within the code chunk? So you'll see that at each of these, I'm giving myself a little title, telling me what this chunk of code is doing. It's setting up the model and testing for normality. This next one is testing for homogeneity of variances. Why am I doing this? I know what each little chunk of code is doing. Why else am I doing it? Down here, where this green section is here, if you click on that, it gives you a table of contents. And so if you want to go back to a particular area or move forward actually in the analysis, you can just click on that and it will take you to that particular code chunk. I want to be at homogeneity variances, so I can just click on that title and it takes me to that code chunk. So here's a tricky thing about Levine's test. There are two versions of Levine's test. There's one that works and there's one that doesn't work anymore. And if I'm recalling correctly, Levine capital T test is the one that works. Let me check to make sure that that's. Sorry. Let's go back before we do Levine's test. What's one of the things you should always do once you've run a test? So we just tested for normality on these residuals. I'm skipping ahead a little bit to Levine's test. What would it be nice to see?
Maybe critical values that are compared to.
Well, the computer does that for us. I mean, you could go and you can take the Shapiro-Wilk statistic and go and compare it to the table, but that just takes time, and it's got the table programmed into it.
What's the p-value tell us again, and how do we analyze that?
P-value is the type 1 error rate. So in this case, we're testing the idea that our data are normal. So if you want to think of it as a null and alternative hypotheses, the null hypothesis is our data are normal. The alternative is they're not normal. And so a type 1 error, in this case, is saying it is not normal when it is. Okay, this is the nature of a type 1 test. In the same way that a type 1 error when you're comparing means is the null hypothesis is that the mean of sample 1 is equal to the mean of sample 2 versus the alternative that mean of sample 1 is not equal to the mean of sample 2. A type 1 error is concluding that they're different when they're not. Type 1 error in this case is concluding that it's not normal when it is. And so P in this case was 0.2164. The alpha level that we're testing this at is 0.05 because we don't want to make the mistake of saying it's non-normal when it's actually normal more than 5% of the time, so we're looking for p-values that are greater than 0.05. So we could say that this is not normal, but we would be wrong 22% of the time.
Okay.
That's our chance of making a type 1
So as long
error.
as long as that p-value is higher than 5, we assume normality.
Yeah, we assume normality. However, as that p-value gets lower and lower and lower, I begin to question more and more whether or not this is truly a normal distribution. Because think about what alpha is saying. Here, we've set our alpha level at 0.05, which means we're trying to avoid saying it's not normal when it is. But as we make that lower and lower, as we have this at 0.05, once again, our probability of making a type 2 error goes up. What's the probability of a type 2 error? What is a type 2 error? It's saying they're normal, when it is non-normal. So we want to be able to say that it's normal, not say that it's not normal. And so some people question, should we really be testing this way? Because this is a test to see if it's not normal, but what we really want is we want to be able to say with confidence that it is normal. And that requires a different kind of testing, which we don't normally think about in introductory stats classes. So yeah, 0.2 is fine. I would be happier if it was 0.5 or 0.9. So because 0.2 is fine, we can say it's not normal. But saying it's not normal is not the same thing as saying that it's normal, if you understand the language of it. And so what might it be nice to look at to give ourselves a little more confidence in this? What do we conduct a normality test on? And if we looked at those residuals, what should it look like?
Pretty uniform.
Not uniform, but it should look like a bell-shaped curve. How can we figure out if it looks like a bell-shaped curve? We can make a histogram. Oh, I should be doing this up there. We can make a histogram. Sometimes R is arcane, sometimes R is not arcane. In the case of making histograms in base R, it's pretty simple. You just ask it for a histogram. A histogram of what? And it gives us a plot. And this plot, how does this plot look to you? It looks normal-ish. This side looks pretty normal. This side looks less so normal. But once again, you're also doing a histogram with only 50 observations, only 50 residuals being plotted. And so it's normal-ish enough that you don't get a significant deviation from normality. But I would have trouble if I was trying to make an argument in a court of law that this is a normal distribution. Just because it's not different from a normal distribution is not the same thing as saying it is a normal distribution. We just don't have enough evidence to say that it's not normal. Yeah. Didn't make a histogram. Oh, let's see. Oh yeah, put up your red sticky if you didn't get a histogram. Oh, that's weird. Did you run install all of your packages at the top?
Well, maybe I think I forgot.
Okay, run that and make sure that did it. If you didn't get your histogram, make sure you ran all your packages. Did that fix it? No, you got it. Okay, all right, cool, awesome. Up at the very top. Go to the very top of your script. You haven't loaded any packages. So Claire, you need to make sure that Pacman is installed, which it probably isn't because we reloaded we reloaded R. So do install.packages Pacman, and then just copy this line of code. So while she gets her packages loaded and tries to get the histogram, what I was saying a minute ago is just because you say that it's not different from normal doesn't necessarily, that's not the same thing as saying it is normal. It's just saying you don't have enough evidence to say that it's not normal. And sometimes that's because you have small sample sizes. Sometimes that's because it's actually just normal. And so you want to always look at your data. So creating simple histograms is usually a pretty good way of going about that. By the way, the worst thing you can do to somebody is look over their shoulder while they're coding. Yeah, there you go. Run that, and that should probably fix things. Now try and do the history. Okay, it's going to take a few minutes because you're installing. Remember that the reason that I use Pacman is so that when you use Pacman, if your package that you're asking it to load is already in your library of packages, it just loads it. If it's not in the package, it will actually install it and then load it. If it's in your list of packages that you already have installed on your computer, it will check and see if you have the most updated version, and will do an automatic update for you. And so that's one of the nice things about Pacman as a utility, is it keeps your version of R up to date. All right, everybody got the histogram. So it's not terribly normal, but it's not super wonky. And so that's good to know. The other thing that we can do is we can run what's called a QQ plot. So now what a QQ plot is it compares what you would expect from a normal distribution to what your data are actually showing you. And so what you do for this is do QQ norm on the residuals. And then do QQ line on, once again, the residuals. What a QQ plot is, and a QQ plot is difficult to think about conceptually. I try and explain QQ plots to my first year biology students, and I don't know what kind of success I have at that, because it's kind of a hard concept. But basically, when you have a normal distribution of data, if you start on this end and move 1 unit to the right, there's a certain proportion that is the area under the curve. And so this is, let's say that's 1%. You move another increment in, you get a little more of the proportion of this distribution under the curve. Let's say that you're now at 3% of the data. Move another similar increment in, you're now at 5% of the data. You move further and further in as you get to thicker and thicker portions of the curve. Instead of increasing by a couple of percentages, you start to make really big jumps in terms of the total cumulative proportion that you've gathered up. As you move from one end of this distribution to the other end, you pick up the biggest chunk right here in the middle, because that's the nature of a normal curve. And as you start splitting this up as you move to further and further to the right, these increments get smaller and smaller and smaller over time. And so what happens is if you look at a graph of the x variable from the lowest values to the highest values, and you look at cumulative distribution that you've captured, from 0 to 100%, what you find is at the beginning of the distribution over here, this cumulative distribution increases really slowly, then it picks up speed, and then as you get past the average, it gets slow again until you finally get to the end of the data set, at which point you've captured the entirety of the data set. And this is what's known as a cumulative distribution curve. The cool thing about cumulative distribution curves is if you take the logarithm of this, it creates a straight line. The nice thing about straight lines is straight lines are easy to see. And so if we take the log of the cumulative distribution from this normal curve, it gives us a straight line, as it turns out. What we can then do is we can go to our actual data and say, okay, starting at the very bottom of our data set, when we hit our first data point, what proportion of the total data set do we capture in that data point? When we get to the next data point, what proportion is then there? What proportion is there for the 5th, for the 7th, for the 10th, for the 50th data point, if we had these ranked from lowest data point to highest data point? If our data set is normally distributed, we should see all of these points on this line. And if all of the points were on this line, our p-value for the Shapiro-Wilk test would be 1. That is a normal distribution. And so one of the other ways that we can look at our data is by looking at QQ plots and basically assess whether or not the data points lie along the line or do they not lie along the line. And they're not going to be perfectly along the line, but there are some ways in which the data are systematically biased that you can pick up in a QQ plot. So for example, if you're comparing your data to a normal curve and your data are skewed right, what happens with skewed right data is here at the beginning, at these low values, do you start to pick up a lot of cumulative distribution or a little bit of cumulative distribution?
A lot.
Yeah, you start picking up cumulative distribution very quickly, and so this whole thing shifts over to the left. What that means is that you end up with a bunch of your data points over here, and it slowly converges at the end. This is how a QQ plot would look if you had what we call positive skew where the tail is on the positive end. If you had a system where you had a data set that was negatively skewed, you would see many fewer data points at the beginning, and you would start to pick up that proportion at the end. And so once again, there are also systematic ways in which your data will deviate from the straight line that points to right skew, left skew, bimodal distributions, all sorts of things. So another way of looking at normality is to generate QQ plots. All right, now I think we've done everything we need to do as far as normality is concerned. So go back down to the homogeneity variances section, and what we want to do is we want to run Levine's test. And Levine's test, in this case, is just Levine test with a capital T. And then once again, you want to do this on whatever your analysis is. And so you could go back up here, and you could copy this whole thing in and put it down here. But since we've already used the assignment operator to assign this model to the term analysis, we can just type in analysis, and when you run that, you will see that the variances are different. So in this case, we ran Levine's test. We got a p-value of 0.003468. What that tells us is that variances are not homogeneous. And this is a problem. It's on the actual data now. Because what the Levine's test does is it takes your actual data, it calculates the absolute values of the deviations from the median, and then it runs an Anova on that.
Right.
So, yeah. I demonstrated this for us back at some time. Let's do head that again. Oh, I don't have it in this data set. Remember when we talked about Levine's test, when we were going through the Anova, I actually had a column in the data set. I think it was for the tick data that showed you what the deviations were, and we did an Anova on the deviations and demonstrated that that was the case. We could do that also for this data set and actually run an Anova on those deviations, and it should give you the same result. Yeah. Okay. Do you have CAR installed?
I downloaded everything up here, so unless.
Okay, let's go down. Let me see. Oh, okay. So go to Levine's test. Where do you have it?
Right here.
It didn't do anything. It's not even giving you.
Maybe if I put it up here.
No. Are you in R Markdown? You are in R Markdown. No, it has to be in a coding block. Yeah, so it won't run. Yeah, see, that's telling you that you have code that's not in a coding block.
Oh, okay.
Wait a minute. You have code that's not in coding blocks there. You also.
All of this ran, so.
Well, that's weird. What are you in? You're in P's, right?
Mm-hmm.
That's weird. Shouldn't. Yeah, get back into that. Yeah, this ran. Oh, it did run. It's running up there, but it's not running there. Delete that code block.
Okay.
I don't know why it's not running code blocks. Because you're in R Markdown.
I can do the blocks later. But
Yeah, okay. That's just weird. Okay, yeah, so you've got it there. All right. Anybody else not get Levine's test to run? Okay. So, variances are not homogeneous. Why is that a problem for us? Rachel, why is that not a problem? Or why is that a problem for us? Elizabeth. Okay, so I'm not a big fan of following rules just for following rules' sake. Practically, why is it a problem for us? Here you have two distributions with different variances. Why does this pose a problem for us if we're trying to tell differences between the means? What are we testing for when we're testing means? So we're testing the mean. So, but is it a test of, what am I trying to say? Well, Karis, just put words in my mouth.
95% confidence interval.
So we're using 95% confidence intervals as a way of making decisions. And when we look at those 95% confidence intervals, let's say that this is the 95% confidence interval for this distribution, and this is the 95 confidence interval for this distribution. Are we comparing overlaps of confidence intervals? What are we looking at instead? Inclusion of the mean. Is this mean included in this population's confidence interval? Is this mean included in this population's confidence interval? No. So are they different or are they not? It's inconclusive. It's hard to make the decision because the decision is messed up because the variances aren't similar. If this population had the same variance as this one, would it be easy to make the decision? Yeah, it would be easy to make the decision. The decision would be that they're different. If this population had the same variance as this one, would it be easy to make the decision? Yeah, and the decision would be that they're not different. When you have radically different variances, it makes it difficult to make this decision of inclusion of the means. So let's go back for just a minute and look at the data as we've plotted it. These are the data. Which one do you think is responsible for this significant deviation from homogeneity of variances? Yeah, the control seems really variable compared to all of the other groups, doesn't it? And so what do we do when we have problems of normality, problems with homogeneity of variances? What are some things that we can do? If we have a distribution of data that looks like this, what can we do with that distribution to make it normal? I mentioned this in passing a couple of times. You might not have picked up on it. Nope. We have the data that we have. We're pretty much stuck with it. We can do a data transformation. What nature of data transformation would we do on this? It's a data transformation that doesn't do much to small values, but brings big values and makes them much smaller. You could take the square root. There's another transformation that you could do, which is take the logarithm of it and does a similar sort of thing. Basically, doesn't change small values much at all, but changes big values and makes them small. In the process of doing that, what it does is it pulls this tail in, and then it transforms this whole distribution into a distribution that looks more normal. And so there are a series of data transformations. There's a whole section in your textbook. I'll try and post where it's at, but you can just look in the index in your textbook for data transformations, and it gives you a series of potential data transformations that are designed for different purposes. And it will basically say, if you have right skewed data, try the logarithm transform. If you have left skewed data, you're kind of just messed up. One of the things it will tell you is if you have unequal variances, there are a couple of things you can try. You can try the arc sine transform, and you can try the box plot transform. Those are both very complicated transformations. This example that I'm working from is from a textbook, and what they came up with is they came up with a really weird transformation. And let me find the transformation. Yeah. So what they did was basically transform the data this way. So I'm going to make a new variable called transdat, which is just transformed. We're going to transform the original data through what is one of the most atypical transformations that I've ever seen. And so transdat is going to be round, because we're going to want it to round, and we want it to take 1 divided by dat $ growth, and we want to round it, and then multiply that times 100. And just to keep order of operations correct, we'll put parentheses around the fraction, and then we're going to tell it to round that to 6 significant digits. So there's the transformation that was in the textbook that I pulled this example from. This is not a very usual transformation. So I'm just telling you that. Don't think that this is a transformation that you can just whip out of your back pocket and do at any point. Look in your textbook when you have data that are not normally distributed or don't satisfy the homogeneity variances assumption, and use those more standard sorts of transformations. When we run this line of code, if we look at the data set again, we can head the data set, and what we should see is we should see a new variable that is the transformed data. And now what we can do is we can run the Levene's test on that new data column. And when we do that, when we do that, I see what I did. I need to modify my analysis. So I have to go back up and I have to get the analysis, because now we don't want it to run the analysis on the original data. We want to run the analysis on transdat. So we have to put the model in here and change growth to transdat. And when we do that, now it should run the Levene's test. And now we have a Levene's test that is no longer significant. So now P is 0.1. Once again, that's not a great p-value if you're trying to make the assumption that the variances are actually equal, but you don't have any evidence to say that they're not different. I'm sorry, you don't have any evidence to say that they're different. And so we could take this transformed data and analyze it as if it were variances being similar to one another. So let's go back and just view the data file. It'll produce it in a table, and we can see that the transformed data all has way smaller variances than it had before. And once again, this is probably due to the fact that we transform this data in such a way that it is a fraction of what it was before. We basically took a fraction of it and then multiplied that fraction times 100. What that will tend to do is it will tend to make, once again, large values smaller and small values will be less altered. So now we need to go back and we need to redo some of the analysis that we've already done. So we need to, for example, rerun the Shapiro-Wilk test on the transformed data. So now, to prevent us from having to retype all that stuff in, let's make ourselves another analysis. We'll just call this analysis 2, and use the assignment operator to then change our model to analyzing transdat rather than the original growth increment data. Then whenever we need to run something, we can just get this new model. So we're going to make a new column, which will be, I'm going to call it transres because it's the residuals of the transformed data, and that is going to be the residuals from now analysis 2. And now when we go and look at our data frame, we should see that there is now a new residual column, and that residual column is different from the original residual column. Put up your green or your blue tabs if you got to this point. Chris, do you need to see other parts of the code? No? Okay. Yeah.
One thing though,
Mm-hmm.
so I accidentally misspelled transdat the first time, so I'd have
That's
a
fine.
column called transstat.
Yeah, that's fine.
But then I put transdat, and then it just kind of added 2 columns
Yeah,
on the same thing.
yeah, that's fine.
How do I delete this one column?
It's complicated. I can show you how to do that.
But it's fine.
But it's fine. Just
Okay.
you can refer to either of those. If you make a typo,
Yeah.
you can just use the typographic error from then on if you want. But yeah, there are ways of deleting columns, which I can show you. If you went through the data manipulation tutorial, you probably ran across it in that. And so you can either go back to those notes or you can come by my office and I'll show you how to do that. So everybody got a new transmogrified residual column. Okay, good. Blue tabs down. So Trenton, what do we need to do next? Oh, come on, Trenton, you can tell me. What are we doing here? We're testing normality. What test do we use to run normality tests? Okay, so just start typing in Shapiro. Guess what pops up? You can use tab complete, and we're going to run a Shapiro-Wilks test on what column of data now, Trenton? Not transdat. Transres, good. And we see that we still have data that appear to be normally distributed. So now we know that we have satisfied the assumption of normality, and we have homogeneity of variances. So guess what that means? We're good to go. We can do the analysis of variance. Now we're going to do the analysis of variance, but we're going to do the analysis of variance on the original growth data or the transformed data? Transformed data. So what is that? That is analysis 2, right?
Why the transform data? Isn't that gonna give us like numbers that we don't want?
Oh, it's going to give us totally whack-a-mole numbers. But they're numbers that satisfy the requirements of the test. What we're going to do is we're going to run the test on the transformed data, and then after we get the answer, we're going to then back transform that data back into the original values of the original data. So let's do that. Let's run Anova on transformed data. In this case, the coding is really simple because we've already given ourselves a model. So get yourself another coding block. And in this case, we've already run the model, so all we really need to do is we need to get the summary of the model. Summary of analysis 2, and what that should produce is it should produce an Anova table that looks different from the Anova table that we had before, but one way in which it is actually similar is it has a very, very small p-value, which means that at least 2 means are different. Do we know which 2 means are different? No, we don't. Would it be nice to see what the data look like in this new transformed sort of way? Yes, it would. If we're going to make a graphic of this, what's the first step that we need to take? What do we normally want to try graphing? Do you want to plot means? Do you want to plot 95% confidence intervals? Do you want to plot standard deviations? Do you want to plot standard errors? You generally want to plot mean and 95% confidence intervals. Where can we get R to calculate those things? You guys remember the syntax for summary SE? You tell it the data frame that you're wanting to get. You want to know what the measured variable is. Which is, in this case, it's going to be transdat. And you want it to what is our grouping variable? Our grouping variable is treatment in this case, right? So let's try that and see if I made any misspellings. Remember, one of the ways to avoid misspellings is by using tab complete. When you have a function, up there, it will tell you what you need to have. So it's going to tell you that you need a data, you need a measured variable, and you need group variables. And so we'll just put those things in. The default is a 95% confidence interval. So what is the data frame? The data frame is dat measure var equals transdat and group vars equals treatment. And when you run that, whoa, made a mistake. In this particular thing, you have to put the variables in quotes. And what you should get out of that is you should get a table that has the treatments, control 2% glucose, 2% fructose, 1-to-1 mix, and the 2% sucrose. It has the averages, it has standard deviations, it has the standard errors, and it has the width of the 95% confidence intervals. Click save on this script. Did everybody get this? Put your blue tabs up if you got this. Did you get it? You got it?
Yeah.
Okay, all right. Okay. Homework for Friday. Make a plot of these data in ggplot2. So this table gives you everything that you need to know to make a plot in ggplot2 because it gives you your treatments, it gives you your average values, and it gives you your 95% confidence intervals. So take a shot, use online resources, use whatever you have at your disposal. Come in on Friday with some form of graphic that attempts to do this. What we'll do is we'll use that as our jumping off point for teaching you some things about graphics on Friday.
What is ggplot2? What's ggplot2 again?
It's just a package that does pretty nice graphics.
Oh, yeah, right.
R has base graphics, but you want to be using better graphics than base graphics. Before you leave, on your tabs, on the orange tab, write down something that went well for you. On the blue tab, something that could have gone... No, orange tab could have gone better. Blue tab, something that went well. I forgot to do that last time. And I will see you guys on Friday. On Friday, I will randomly pick one of you to present your attempt at a graphic. So come prepared for that. If you have questions between now and Friday on how to get started in ggplot2, feel free to drop me an email, and I'll do my best to help you through it.